Let's get started. Welcome everyone to this first session, afternoon session of the Biomedical Imaging School. Today we're very happy to welcome Amaury Badon from Bordeaux. Amaury did his PhD at the Langevin Institute in Paris and then went for a postdoc in the Merz group in Boston University for a few years where he worked on multiplane imaging, microscopy.
Yep.
And today he's in Bordeaux and the group of Pierre Nassois working on optical microscopy to image organoids mostly. And today he's going to give us a course, introductory course on optical imaging. Thank you very much, Amaury, and the floor is yours.
Thanks, Thomas. Thanks for the invitation. I remember 7 years ago when we were both students attending a school here. Okay, and today I'm in charge of this introduction course on optical imaging, and more specifically on optical microscopy. So first, why do we use optical microscopy? And for my understanding, this is a drawing of a cell. Okay, so sorry for the biologist. But the aim of optical microscopy is to observe with your eyes what is usually invisible to your naked eye. And the first idea is that if we take a cell, it's only 10 microns in size, and the eye limit is around 50 microns, so depending on your age. But usually it's half of a hair, so around 50 microns. And so usually cells are too small to be seen with your eyes. Also, cells are quite transparent. So in transmission, the light cell interaction is too small, and so basically you will see nothing. But sometimes when you want to target a cell which is embedded into other cells, now the cells is too opaque. And so you want a microscope to be able to observe the cells which will be small, which can be transparent, or can be inside an opaque medium. And here I will mostly talk about this regime of optical microscopy, where we have a resolution which is usually of the order of 1 micron, which is the wavelength of the visible light, and a penetration depth that can be up to 1 millimeter at most. But it has been a long journey to go to a conventional microscope. And actually, it first started centuries ago with Hooke, which is the, so sorry for the Dutch people, but it's supposed to be the first published observation with a microscope. So there is a debate, but you can see with Nature milestone in microscopy if you want to complain. But basically, in the 16th centuries, Hooke used a microscope, which actually looks like a conventional modern microscope, and it was the first observation of cells. Here it was cork cells, and he published a manuscript with these drawings made by hand. But now, so a few centuries after, we are in the domain of super resolution, where now we can claim nanometer resolution or even below angstrom resolution, as claimed recently in this paper. So of course there have been a lot of different milestones in between, and so we can cite diffraction limit theory in the 19th, but more recently, and techniques that we are now using on a daily basis, we can cite confocal microscopy or two-photon microscopy, or now super resolution since the last 2 decades. And to cover a part of these milestones, this is the outline of my course. I will first start with the principle of a conventional microscope, and then we'll see how to image 3D specimens, how to go deeper, and the use of optical sectioning to do this. And we finally will see how can we increase the amount of information captured by an optical system. So I will not cover a few topics because it's too broad, especially in no deep learning. There is a session on AI in imaging that will probably cover this. And but this is really a growing field in microscopy. And also I will not talk about true super resolution techniques such as Cette, Palm. I will stick with more conventional imaging or techniques that can increase the resolution. Okay, so we can start with a regular microscope that you can find in any lab. And basically, the 3 important parts are the excitation, the samples, and the detection. So the excitation, you have a broad variety of light source. You can use it in a bright field mode, you can use a laser, you can use a lamp, you can have a structured illumination, as we have seen this morning, in X-ray. For the light sample interaction, we are mostly interested into absorption, scattering, but we have also fluorescence, or non-linear effects. And finally, the detection of your microscope. So it can be, you can detect transmitted light, fluorescence light. You can use several detectors, such as camera or photodetectors. And basically, the detected signal of your system depends on these three factors. So here it's a cross, but it doesn't mean that it's a multiply sign. Sometimes it's not as simple as this. And to explain basically the how a microscope works, we can start with a bright field microscope, which is really the simplest one. So a bright field microscope, actually you can remove the factor of illumination because you have a spatially constant illumination. So you illuminate a sample, and simply you have a microscope objective, you have a lens, and usually you have a detector or camera. And what you see is that in the sample plane, you put an object. So here this is a multicellular aggregate. And on the camera, what you observe is a magnified object, but you observe only the intensity. Okay? In optics, we have only intensity detectors. We don't have access easily to the field. But to understand how it works, usually you take a subdiffraction bead, and when you image this, you obtain an enlarged image of this bead, and this is called the point spread function of your microscope, or the impulse response of your microscope. And this, you can easily calculate it for the bright field microscope. I'm not going into too much details, but the idea that we take usually is to consider a microscope objective, which can be rather complex, okay, because here this is a cutoff of a microscope, and you see that there are like plenty of lenses to correct for various aberrations, to correct for various colors, but the idea is to consider this as a single lens. And a lens actually just performs a spatial Fourier transform between the focal plane and the pupil plane, which is placed after. And first lens is performing a spatial Fourier transform, and it introduces some spatial frequencies, which scales with lambda's wavelengths and the focal length of the first lens. And then the second lens is performing the same operation, spatial Fourier transform, but now you are dealing with other spatial frequencies, and now you are introducing the focal length of the second lens. And all in all, if you do the math, basically you do two spatial Fourier transform, and you obtain simply a magnified image with the magnification factor, which is related to the ratio of the two focal lengths. So simply you can interpret your microscope as a magnifier with these two parameters. But if you go into more details, actually a lens is not performing a perfect spatial Fourier transform because it has a limited size. And so basically you are not doing an integral over all the rays, but you have limited size and you have diffraction effect. And when you focus a beam with a lens, you don't have a perfectly thin point, but you obtain an airy disk, which is a spatial Fourier transform of a pupil aperture. And with this, you can introduce some diffraction size and resolution limit. So usually we use something which depends on the refractive index of your medium, on the wavelengths that you are using, and divided by the numerical aperture of your optical element. So the numerical aperture is just depends just on the diameter and the focal length of your optics. And with this, basically, if you want a better resolution, you take a large numerical aperture, and if your numerical aperture is close to 1, you end up with a resolution of the order of the wavelengths. You can do better, and if you are using some blue light, basically, you can end up with a resolution up to 200 nanometers. So a bright field microscope, the image actually is, you have your PSF, you have your object, you convolved it, but you are measuring an intensity, so you take everything square. Now you have your image. The contrast of your image is simply absorption and scattering. So if you have nothing, you have some bright signal. If you have some matter that absorb or scattered light, you have some gray or dark areas. So this is the main contrast mechanism in bright field. The resolution, as I said, can be down to 200 nanometers. And the acquisition speed can vary, so it really depends on your camera, but you can easily go to 100 or 1000 hertz, especially in bright field as you have plenty of light. And the field of view, it depends on your optics, but it can be a few microns, but up to 1 centimeter. So this is basically the regime where we work. Okay. From this, we can just do some slight modifications and obtain actually some striking different images. So the first one is a dark field mode, which is also present in most of the commercial microscopes that you have in your lab. And it simply consists in modifying the illumination PSF. And I don't know if you see it clearly, but basically you shine light with large angles on your samples, angles that are larger than the collecting angles accepted by your microscope. And basically you cannot collect this straight light, and you collect only the scattered light, as we saw this morning. And you can have these nicely contrasted images with the dark field mode. We can also do easily some phase microscopy. So it's a little bit more complex. You need to modify a little bit both the illumination and detection. But the idea is to have interferences between the scattered light by your sample and the background light. And by doing this, you can increase the contrast, and from an intensity image, regular intensity image in bright field mode, where you see almost nothing, because these are 2D cells culture, so it's really transparent, so you have a low contrast, but in the phase mode, you have really a nice contrast, and you can clearly see individual cells here. So now, on a simple microscope, we can also change the sample light interaction and have a different modality. So one of the simplest of the modality is the epifluorescence microscopy, where you still have the same excitation and detection as previously, but now you are dealing with a different interaction. So the idea here is to use some molecules that have some fluorescence properties, and basically they can absorb some photons at a given energy level, and then they can produce some fluorescence light. So usually, so here it's a blue light that is absorbed, and a green light which is emitted. So of course, the emitted light has longer wavelengths than the excitation due to energy conservation. So the most common fluorophores are of these colors, and you excite it with a blue laser. Here you produce some fluorescence on your sample, and then you back collect a part of the fluorescent photons that are going through a dichroic mirror, and then you collect it to a microscope. So a good thing here is that due to this, what is called a stock shift, you can separate spectrally the emission and the excitation. So you have usually few tenths of nanometers in wavelengths between these two peaks. And basically, if you put a cutoff right in the middle, you can still send the blue light to your sample, but only collect the green light on your detector. And by doing this, you can have in a wide field mode, meaning that with a camera, in a single shot, some fluorescence images. Of course, you need a different source. So now you need some more powerful sources, because fluorescence has a low yield. So usually you have a low number of photons compared to what you are exciting. And you need to add more optics in your system. So you need filters, you need a dichroic mirror. And of course now, you can work directly on your sample. So some samples are autofluorescent, so meaning that you don't need to add any label. So for instance, a lot of plants are autofluorescent in the UV or in the blue light due to the chloroplast or other structures. But you can also add some specific markers to see some structures. And so this is what I said. So this is autofluorescent tick, actually, in a wide field mode. So here you don't have any structural information. Basically, you see the whole samples. But then you can also have some different markers that can be dynamic. So you can do, for instance, a lot of calcium imaging, especially in the mouse brain, for instance. And here, basically, you have the neurons are emitting fluorescence, only where there is some calcium activity, calcium exchange, meaning that there is some brain activity. And you have here some dynamic information. So I'm not going into too much details because you will see this, I think, tomorrow or in 2 days, tomorrow. But also, you can, still in a static domain, you can do some multiple specific labels. So for instance, here, this is a multicellular aggregate, and you have plenty of colors corresponding to plenty of different labels. So meaning that here, here we are using only one wavelength, but you can use multiple wavelengths at the emission. And if you have the correct filters, you can, by doing this, have different colors. And here, each color corresponds to different type of cells or different structures. So for instance, here, these are adipocyte cells. They produce fat. And what you see in yellow, these are just oil droplets that are present in these structures. So this is actually a pretty thick sample. This is like 300 microns in diameter. And most of the biological samples are in 3D. So it can be embryos, it can be aggregates, but it's in most of the cases, it's not a 2D structures. But a microscope actually is made to capture only orthoscopic views, meaning that you have a sharp image of a 2D plane, which is orthogonal to your objective, but you don't have a sharp information on what is above or deeper. And usually, what you do to observe the 3D structures is simply to move your objective or to move your sample. Okay? And if you do this, for instance, in bright field mode, so this is a multicellular aggregate, once again, which is encapsulated into a gel. And basically, as we are going through the focus, we see that on the side, where there is only the shell, we can nicely retrieve a sharp image. But on the center, we have plenty of cells, and we are not able to see different planes, different structures. Okay, so this is due to scattering, and actually, this techniques works only with transparent samples or semi-transparent samples. Basically, here we see contributions from plenty of planes in our sample. So basically, in order to retrieve a 3D information on our sample, we need to perform what is called optical sectioning. And to explain what is optical sectioning, I like to use a microscope in reflection mode, but still with the same wavelength. So basically, we shine light on a sample, and then we collect the reflected light, and we measure it on a camera. And if, let's say that we aim for a target which is at a certain depth, basically, we have different trajectories in our sample. We have in blue our signal of interest, which is single scattering. Basically, we have a ballistic propagation from the objective to the target. Then we have a reflection on the target, and we have another ballistic propagation. But of course, we also have plenty of multiple scattering contributions, which we are not interested in. And what we collect actually is the sum of these two contributions. We have the single scattering contributions and the multiple scattering ones. Oops, sorry, I missed the colors. But the ability to image the target, if we have this, is just given by, let's say, the contrast that we have. And this is defined by the ratio of our two contributions. So single scattering over multiple scattering. And in this regime, if you compute this, what you see is that the single scattering is exponentially decreasing. And this exponential is governed by basically the depth of your target divided by scattering mean free path. So this length is really a characteristic of your medium, and it's defined as the mean distance between two scattering events in your sample. But this means that quite deep, because it's an exponential, you are not able to image. and quickly the multiple scattering is dominant. The multiple scattering is characterized by its albedo, or multiple scattering reflectivity. And this actually is I don't know if you see it, but it's governed by the scattering mean free path divided by the depth of your sample, or by the thickness of your medium. So basically, this is exponential, this is linear. And so at the end, if you compute this single to multiple ratio as a function of the optical thickness, which is this distance, then you see that you have an exponential decrease. And so if you put your detection threshold as 1 for this ratio, you see that very quickly multiple scattering is dominant. And then you don't see your target anymore. And in practice, let's say that the limit is around 1 and 2 scattering mean free paths. And depending on the organ you are imaging, this can be 10 micron or 100. It really depends on if it's a brain or if it's a liver, so it really depends. But this is pretty shallow, okay? And so of course the idea is we want to increase this ratio in order to image way deeper. And to image deeper, the simplest solution, because we have here a ratio, so we can increase this single scattering contribution, but actually this is pretty hard to do, or we can reduce this multiple scattering contribution. And rejecting or reducing multiple scattering light, this is what is called optical sectioning. And there are plenty of different techniques to do it. So you can do it in the temporal domain, as is performed in optical coherence tomography, for instance. Or you can do it in the spatial domain, as it's done in confocal microscopy, for instance. So I will start with a spatial domain and with this illustration, because actually in SIG sample, you don't collect light only from one plane, but from various planes. So here, if you are in focus, basically you collect some light and it will be focused on your camera. And so you should retrieve a nice PSF, so you have a thin image on your camera. But actually you are also collecting contributions from deeper and from shallower. And from deeper, as you see, the image is actually refocused before your camera and then expanding again. And so it means that on your camera, you see like a broader image, even if you had a point at the beginning. And so this image also can be degraded if you have scattering, but actually it's quite different from what you expect if it's in the native focal plane. But you have also contributions from shallowest depths, and here you have also a broader spatial response. And so at the end, if you are doing, for instance, fluorescence, and you have like a thick sample, so for instance, culture of neurons, this is a typical image you get in wide field fluorescence microscopy. So you see some details, you see some neurons, but it's pretty blurred, okay? This is due to the contribution of different planes. And what you want is to have something quite sharp, with nice resolution, nice contrast, as obtained in confocal microscopy. And so how do we obtain this kind of image? The idea is to do some spatial filtering of the detected light. So here, in the epifluorescence conventional microscope, you collect all the light with a camera. And so you have, even if you focused your illumination as the input here, ideally you would like to collect something similar to your excitation. But actually, when you go deeper and deeper, you are collecting a broader response. You have scattering, you have autofocus. And so the idea is that you know what you expect to have. So basically, you put a spatial filter and you select only the central part of what you are supposed to measure. And this actually, you can do it very easily with what we call the pinhole. So it's just some absorbing part with a hole in the middle, okay? And depending on the size of this hole, you will select more or less scattered photons. And so this is really the principle of confocal microscopy. But of course, with this, you have only one point. You have one spatial point, and the idea is to have a 2D image. So how can we build a 2D image? So the simplest way, and it was used for decades, was to move the sample. So basically, here you have one point, and you move your sample in X and Y direction, and you can build an image. And this works fine, especially because you are imaging right at the center of your field of view, where you have no aberrations. So it works fine, but this is very slow. So it takes minutes to build an image. And if you want to do some in vivo live imaging, this is way too long. And so the second solution is to move the scan beam. And here, the idea is to use the Fourier relationship between the focal plane and the pupil plane. And basically, by simply doing a tilt in the Fourier plane, this is converted into a shift into your focal plane. So this is way faster. You can go to kilohertz. You can really image over a large field of view. It's more complicated, it's more expensive, and you can have some aberrations on the side of your objective if you are using angles that are too large. So this is what a regular confocal looks like. So you have a laser beam, which is focused on a given point. Then here you have a mirror, which can be tilted. And with this tilt, you can move your focus. Then the fluorescence light is collected, is descanned, and is sent to a pinhole. So it's important that the light is both scanned and descanned, otherwise it will hit different parts of your pinhole. So it's a point-by-point image formation, and you are using a resonance scanner. So now resonance scanners can go up to 8 or 10 kilohertz. So this is pretty fast. Actually, this is also in the audible range, so it can be quite annoying to hear it, especially if you're young. And with this high-speed resonance scanner, you can build images which, let's say, are 500 by 500 pixels at 30 Hertz, which is called video rate in microscopy. And so with this, you are pretty happy. You can see pretty large samples quite easily. So for instance, this is a mouse brain vasculature. So here, basically, you put some labels inside the veins of a mouse brain, of a mouse, and then you can see the veins. So with such a speed, actually it's fast enough to capture some calcium activity in various animal brain. So you can do it in mouse brain. So this is a raw data where you see plenty of different neurons. These are like something like 1,000 neurons firing at different times. And here, these are the temporal traces. So basically, you see that this is the evolution of the fluorescence as a function of time. And you see that you clearly see some peaks. So it's fast enough to measure the brain activity. You can also do some other animals, like C. elegans. This is worms. So it's semi-transparent, so it's very used a lot in microscopy. And you see different neurons firing at different time. So this is pretty good for plenty of applications, but it's still too slow for specific applications, such as voltage imaging, where you need to be like really orders of magnitude faster than that. But also confocal microscopy is limited by its phototoxicity. So why? It's because it's a point-by-point technique. And so as you want to be fast, you want to spend really a small amount of time on each pixel. But you need a sufficient signal. So basically, to have a sufficient signal in a small amount of time, you send a lot of power. And usually, it produces phototoxicity and photobleaching, meaning that you lose your signal, which is photobleaching, and you kill your sample, which is phototoxicity. So to reduce this phototoxicity and to go faster, few decades after confocal microscopy, there had been a proposition to use a parallelized version of confocal microscopy, which is called a spinning disk. And so the idea is, instead of using only one pinhole, you use an array of pinholes. And by doing this, you have plenty of different points of your sample at the same time. So here you are not using a scanner, but you shine your light through two spinning disks to two disks that have holes. And so by doing this, you are exciting fluorescence on your sample only on sparse points on a sample. And then you back collect the fluorescence light through the pinhole to have optical sectioning, and then you send it to a camera. And for a given position of a disk, you fill a part of your image. And if your disks are now spinning pretty quickly, you can fill an image pretty quickly by doing this. So you use a high-speed camera, meaning that with a high-speed camera and really high-speed spinning disk, you can go quite fast, and basically you can win a factor of 10 compared to regular confocal microscopy. It's better and better because now CMOS are really sensitive. Like decades before, we were using CCD, which were not really, CCD are slow, but before CMOS were not as sensitive as they are now. So now they're really comparable to photodetectors. So it's really sensitive. The only drawback is that you can have some crosstalk between neighbored pinholes. So basically, if you are going deep, the light from one position can be scattered and can enter another pinhole. And this can reduce the imaging depth that you aim. But still, even if this is a really interesting techniques, you have some phototoxicity because due to the optical sectioning, we detect only one part of the emitted fluorescence. So basically, we excite with a relatively large Gaussian beam, so meaning that we produce fluorescence from different depths, but with the pinhole, we detect light only from regions near the focal plane. And so this is useless. Basically, you are producing fluorescence light over and over in your sample, and this will produce photobleaching and phototoxicity. So an idea to avoid this is to change the geometry and to do some selective plane illumination. So by doing this, you want to illuminate, to shine light only on the region that you are currently imaging. And so to do this, you need an orthogonal geometry. So here you have a regular fluorescence microscope, but now the illumination comes from the side. And by doing this, you can spend more time on each pixel, meaning that you can reduce the amount of power, so you have a gentle excitation. You image directly a 2D plane, so you can use a fast camera, meaning that you can increase the imaging speed. The lateral resolution of your technique is just given by your optics, so it can be pretty good, it can be sub-micron. The only drawback can be that now your axial resolution does not depend on your optics here, but it depends on the size of the thickness of your light sheet. So basically here, if you have your objective, you will produce fluorescence from a sheet of light, and your resolution will be given by this thickness of the light sheet. So in this technique, the key point is how to produce, how to generate a good light sheet. So there are different strategies. The simplest one, which was the first one, was the use of a cylindrical lens, which is a particular lens that focuses light only in one direction. And if you put this on the orthogonal direction, you have directly a sheet of light. So it's simple, but it works okay for a moderate resolution. Basically, your sheet of light will be pretty thick. There are other techniques, and one of the best ones is the use of a single beam that you scan pretty quickly. So here you can generate various beams that are focused only on one position, and the idea is to scan it very quickly, so faster than one exposure of your camera. And so your camera just sees the average motion of your beam, and it sees a light sheet. For this, you can use various types of beam. So usually in microscopy, we deal a lot with Gaussian beam. But with Gaussian beam, the lateral and axial extent are directly connected. So if you want to have a sheet of light which is extended in this dimension, basically you will lose a lot in the lateral sense for the Gaussian beam. So here, your sheet of light will be really thick, so it will be useless. So usually people are dealing with other types of beam, and mostly with Bessel and Airy beam. And Bessel beams are pretty useful because you see the axial extent of a Bessel beam is really large compared to Gaussian one, but you have actually a comparable thickness of the sheet. The only drawback is that there are a lot of side lobes. So actually there is a lot of also energy in these side lobes, and this can produce some photo bleaching. But this is pretty small compared to confocal and to spinning disk. And so typically, light sheet now is really the ideal candidate to observe embryos because you have a high temporal resolution, so you can really see sub-second events. There is low phototoxicity, so you can image really at high speed over a few seconds, or you can image over minutes or hours or days the development of embryos, and you have a high spatial resolution. And so typically, if you take some embryos, you can have this kind of videos in fluorescence. So this is XY, and these are the projections. And basically, you have a sub-resolution, subcellular resolution, and you have a nice temporal resolution. And this, you can run it for hours and hours. There is no phototoxicity, or very small amount. Actually, there is a main limitation of this light sheet microscopy is that if you use only one objective to produce the light sheet, your samples can scatter the light sheet. And this will end up with attenuation of the light sheet, meaning that on your image you will have one bright side and one dark side. So you don't want this. So you can correct it by using two objectives facing each other. By doing this, each one is sending a light sheet, and you can compensate for this attenuation. Of course, this is more complex, so you need some nice alignment of your two objectives. And most importantly, then you don't have a lot of space to put your sample in the middle. Especially if you want high resolution objectives have like small working distance, meaning that here, in between three objectives, you have only few millimeters to put your sample, and so this is really for small embryos or for small piece of tissues. And so to fight this issue, recently there have been some development on single objective light sheet microscopy. And so here you use only one objective to both produce a light sheet and detect the fluorescence. So here you produce a tilted light sheet by basically having some incoming light with an angle, and you collect light from this light sheet. So here you don't have any problem to access your sample. So you can have 6 samples, you can have embryos, but it's actually even more complex than that on the detection part. Because if you, right after your microscope, you have a tilted image, and you want to tilt it back to project it onto your camera, and to tilt it back at high spatial resolution, the idea is to use some remote objectives that are tilted, and you need to do it at a micrometer scale. And so apparently this is a nightmare. With confocal microscopy or spinning disk or light sheet, basically you increase the ratio of the single scattering over the multiple scattering by a factor n being the number of spatial degrees of freedom in your system. So basically it's the number of cells in your image, and by doing this the ratio increases a lot, but linearly. So as it's an exponential decrease, actually you don't win that much. But typically, with a confocal microscope, depending on the medium, but you can image up to 100 microns or 200 microns if you have a good label and if your medium is not too opaque. So this is better, but this is still quite shallow, especially if you want to do some brain imaging. You don't have a lot of neurons in the brain at this depth. You want to go way deeper. So there are several strategies to increase this imaging depth, still with a confocal microscope. And so the simplest idea is to increase the wavelength. Because here we are dealing mostly with visible light, Okay, but the optical window actually is more in between the red wavelengths to the near infrared. Optical window is where the attenuation in biological tissue is less important, basically. And so you have mostly water and melanin. And what you see is that if you go to red or near infrared, you have the relative absorption that decreases a lot. But to do this, you need to have some dyes in the red for the red wavelengths. So this is a big stake in chemistry to develop good dyes in this regime. Also, you can even go deeper and go to near infrared. So for instance, there has been this recent paper which showed that by using 1.7 micron laser, so really even to the right than this, longer wavelengths, you can image at around 1 millimeter in the brain. So of course you lose a little bit of resolution because you increase the wavelengths, so you lose a factor 3 of resolution, but you can image really deep. The issue is that you need some specific optics at this wavelength because usually good microscopes and good cameras are for the visible light, not in this region. And also there are no dyes at this for this wavelength. So you are not using fluorescence, you are using the reflected light to image at this depth. Sorry. So before it was a one photon sample light interaction, so we were limited to 100, 200 microns, but we can really increase the imaging depth by using a 2 photon interaction. So this is a comparison of 1 and 2 photon fluorescence, where in the previous case, as I said, we are producing a lot of fluorescence above and below the focus of your objective, of the focal plane. So basically, you want to focus here, but you are producing a big amount of fluorescence, of out of focus fluorescence. So this is, and you can clearly see it on this picture. This is not the case in the two photon fluorescence. And basically here, this is a non-linear effect, and you see that you have only a small dot at your focus. You completely removed all of the out of focus fluorescence light. So this is, I will not spend a lot of time because you will have a talk mostly on it, but basically as it's a non-linear effect, you need a high power to produce some signal, and in the other regions you don't have this amount of power to do it. And actually you are using several effects to image quite deep in 2 photon. The first one is that you are using near infrared excitation. So as I said, we can go way deeper with near infrared excitation. You have a deeper penetration. And the good thing is that you can use the same dyes as in confocal microscopy because you just double the wavelength compared to the regular confocal. So now you need 2 photons, but basically you achieve the same absorption level. And a microscope, a 2 photon microscope really looks like a confocal. You have now a pulse laser. You shine light onto your sample. You collect the fluorescence light onto a photodetector. So you need a pulse laser because it's a nonlinear effect. You need a lot of power. So basically, you win a lot by compressing your intensity into pulses. This is what is called the compression factor, and basically you increase by this amount of signal the fluorescence by using a pulse laser. But here, compared to confocal microscopy, you are not using any pinhole. So there is no spatial optical sectioning in the detection. Basically, everything is done at the illumination. So the claim is that you are not producing any out of focus light, so there is no need for pinhole. So you just use a large detectors to collect as much light as possible. And by doing this, you can image really deep. So this is a cleared mouse brain, but if it's not a cleared mouse brain, you can image usually up to 800 microns or 1 millimeter, which is already quite impressive compared to a regular microscope. This is already pretty good, but two-photon microscopy is still limited because even if you are using near-infrared light, you have still some absorption, you have still some scattering, and if you want to image at 1 millimeter, the amount of power non-scattered start to be low, and so this is limiting you. And also, as you are using quite powerful laser, you are producing a lot of still some fluorescence from shallower depths. And so two-photon microscopy is limited by these two effects. And to go deeper, actually, recently, there's been the development of three-photon microscopy. So now you are using even lasers which are even more in the infrared, so in between 1.3 and 1.7 microns. And with this, you can image really, really deep in the brain. So for instance, this is a video. So this is basically this, but plane by plane. So here you see the depths, and you see blood vessels, you see neurons, and you can go up to more than 1 millimeter. But here it's not a cleared mouse brain. So it's really in vivo. And you can even, because it's quite fast, so you can even do some dynamic measurement. And this is currently the limit of what we can do in microscopy in depth. But actually, everything that I showed, it was cheating a little bit, because even with 2 or 3 photon, we cannot image the skull, or really rarely. So usually, what is performed is a cranial window. So we remove the skin, we remove the skull, remove a part of the brain, and we glue a cranial window, which is transparent, and then we can have direct access to the brain. This is stable for months, actually, so you can image it really every day for months. And if you want to image even deeper, so you can also remove part of the brain to image some deeper parts. And once you have done this, then you can do different imaging techniques. So you can do regular microscopy by head fix your mouse. So now you have access to a large part of the brain. But also what is more and more developed is some miniaturized microscope that can do everything that I showed before. So confocal, 1 photon, 2 photon, or bright field. But everything miniaturized, meaning that it's only, I think, 3 grams or maybe lighter than that. And it's really on the head of the mouse. You just have some wires for the laser beam. And the mouse can have a free behavior while you are recording the activity. But of course, with this, you have worse optical performances compared to a regular microscope. But you can still image thousands and thousands of neurons at a decent speed. Okay, so I think we did everything we can to image in depth by rejecting multiple scattering light in the spatial domain. So we even remove a part of the sample. So now we will see what we can do in the temporal domain. So in the temporal domain, now we need, for the picture, a pulse source. And we want to see the difference of signature between single scattering and multiple scattering. So in the single scattering regime, if we send a pulse, we have, let's say, a target which is reflecting. And what we receive is just an echo at a time which is directly related to the depth, 2 times the depth divided by the velocity of the wave. But this is not, of course, not the case if we have multiple scattering. So now we have plenty of different trajectories, meaning that now we have a very broad response. And what we want to do is we want to extract the specific time to retrieve the signature of our echo. So we want to select a given temporal window. But before that, we need to have numbers. And in scattering media, let's say that if we take a scattering mean-free path of the order of 100 microns, this gives you a typical scattering time of 3 picoseconds. So this is pretty fast. And now if you want to do some time gating with this, you can do it directly with fast detectors, or you can do it indirectly. And direct time gating with fast detectors actually is pretty challenging, because if you take really good strict cameras, they can go up to 100 picoseconds. This is already pretty fast, but you see this is still orders of magnitude longer than this typical time. So basically, even if you use this kind of strict cameras, you will not be able to nicely select single photons over multiple, single scattered photons over multiple scattered photons. So usually what we do is we do some indirect gating using some coherence. So here this is an interferometer, and if we have a pulse source that we send to this interferometer, we split the light in between a sample and the reference, and then it's reflected, recombined, and we have a detector. And depending on the position of these samples and reference, we will see interferences if we have the same path length, or no signal if there is not the same path length. And by moving the reference or the sample, we can measure like this echoes. And this is the optical equivalent of ultrasound echography, where you just send a pulse to a medium and you measure an echo. Here, you get the depth information from the time of flight, as in ultrasound echography. But here, the source is quite important, because it gives you both the ability to do some optical sectioning to reject multiple scattering light, but also it gives you the axial resolution of your system. And you can compute the size of the temporal window. This is given by the coherence time of your source. And so there are some prefactors, but basically it's inversely proportional to the bandwidth, to the wavelength bandwidth of your source. So the idea is to have the broadest source as possible. So it can be superluminescent diode, it can be LED, or it can even be a halogen lamp like we are using in this room. And one of the main techniques that is using this gating in a time domain is optical coherence tomography. And this is really used to study the human eye. So in most of the hospital, you see this kind of machine now. And you can, so this is an en-face image, and this is an in-depth image. This is a cross-section image where you see different features of the human eye. And of course we want the broader source as possible, and so superluminescent diode usually they have a bandwidth of the order of 10 nanometers. So this is already pretty good, but you have an axial resolution which is of the order of 15 microns. While if you are using LED, so it's really low-cost sources, you have a way broader spectrum, which gives you some axial resolution that can be sub-micron. Which is quite nice. And then by just building a small interferometer, you have a LED, and then you just shine light on your sample, you collect the reflected light, you do the same with the reference mirror, and you measure the intensity between your two arms. So it's really like a Michelson interferometer, but with just two microscope objectives. And by doing this, you can do the equivalent, the optical equivalent of ultrasound echography. So here the contrast is the structure of your sample. So there is no specific markers. Here you just see if you have some medium or not, basically, some absorption or not. This is a non-scanning technique, and this is really simple and low cost. And this is the kind of image that you get. So basically here what we see is, once again, some encapsulated cells embedded into a gel. So this is the gel that you see. And actually, these are stem cells. And stem cells, when they are happy, they are forming cysts, which is kind of a balloon. So there is only one layer of cells, and then inside it's a balloon. So we studied this a lot in the team. Okay, so I did not put two-photon microscopy on this graph because it's rather complicated to compare. But if you do now optical coherence tomography, so which combine actually optical sectioning in space and in time, you are increasing again your single to multiple scattering ratio by a factor which depends on both your source and both on your medium. So this is now the time-dependent reflectivity on your medium. So basically, this is governed by diffusion. But the idea is that if you use a broader source, you will have a significant gain on this curve, and you will be able to image deeper. So typically, optical coherence tomography, or OCT, can image up to 500 or up to 1 millimeter into biological tissue. Okay. So before I told you that the ability to image was given by the single scattering over multiple scattering. So until now, we mostly deal with rejecting multiple scattering. But actually, we can do a little bit on the single scattering. So we'll see how can we increase this contribution. And also, we'll deal about aberrations, because we only talk about single scattering, multiple scattering, but in between, there is a kind of a blurred range with aberrations and with slowly varying scattering. So if we take an objective, in the ideal case, we have a plane wave, and this will focus onto a sharp spot. Now, if we add an aberrating layer in between your focal plane and the objective, it will distort the wavefront, and you will end up with a degraded focal spot. So the idea of adaptive optics is to perform before the medium some aberration correction. So basically, you will preform your wavefront in order to compensate for this aberration and to retrieve a nice focus behind your scattering or your aberrating layer. And so now this is quite used in microscopy, but actually it was invented or proposed decades ago in a totally different domain, which is in astronomy. Yeah. So it's back into 1953 by Babcock, who's proposed this idea of shaping the surface of a mirror to compensate for turbulences, to compensate for aberrations. So the initial idea was actually to put some oil on top of a mirror, and by playing with an electric field that was varying in time and space, you can correct for aberration. But this was never performed with this technology, but with a different technology. And so the idea is that if you have twin stars that are literally at the infinite, then when it's coming to Earth, you have a nice wavefront, you have plane waves, but then you have turbulences in the atmosphere. And this will severely distort your wavefront. So this is why astronomers like to put telescope not on Earth, but in the sky, is to avoid these turbulences. And so because of this, your image is blurred. And so the idea was to introduce a deformable mirror here to correct for this aberration, to retrieve a nice plane wave that will give you a correct image of the twin stars. And so it took more than 20 years between the initial paper and the actual implementation using this deformable mirror. And this is an example of what you have without. So this is images of Uranus at 2 different wavelengths, and you see that it's quite blurred due to these turbulences. And if you apply a correction, then you retrieve a really nicely contrasted image. But you need some information on the turbulences. And actually, this is quite jealous of this, but in astronomy, they are using these huge lasers to do some fluorescence, actually, after the atmosphere. So basically, they need to characterize the turbulences. So what they do is they shine the big laser onto a sodium layer, which is after the turbulence. And here, they measure their image, and they know that this is a point source. So now, they try to find the good combination on their deformable mirror to retrieve a sharp image of this guide star. And now the idea is to do the same in microscopy. So in microscopy, this is quite different because our object is not at the infinite, but it's in the focal plane of an objective. But the idea is similar. So basically, you have illumination, so you have your light beam, and here you want to focus after an aberrating layer. And so your focal spot is pretty bad. It's degraded. And so the idea is to deform this mirror in order to refocus your light. The good thing is that here we are imaging in reflection. So you are correcting, if you find the good correction, you are correcting both for the illumination, but also for the emission light, for the fluorescence light or for the reflected light. And when you do this, you can really retrieve a nice contrast. So these are images of synapses in depth in the mouse brain, and you see that without adaptive optics, you see nothing. And with, you can nicely retrieve some images of synapses at really high resolution. So here we have a sub-micron resolution. But we need to find the correct deformation for the mirror. So there are two ways. The first consists in a direct measurement, and the second in an indirect measurement. So the first one basically consists in using a wavefront sensor. So a wavefront sensor, or a Shack-Hartmann, this is just a micro lens array in front of a camera, and you have an array of dots. And depending on the aberration, this will just gonna shift the position of the spot. And with this, in a single shot, you measure the wavefront of your light. So this is really fast. So this is really the advantage. But the drawbacks is that it works only with small distortions. If you want to go deeper, then you don't have only ballistic light, but you have a lot of scattered light, and here you are not able to perform some aberration correction to find the correct wavefront. So in this case, when you want to go deeper, what you do is you do an indirect measurement. So you have your deformable mirror, and you segment it into different areas. So depending on the strength of your aberrations, you can use 10 by 10 or 100 by 100 segments. And for each one, you will iteratively try to find the correct position to increase your signal. So this is quite time consuming, because let's say that if you have 100 segments, for each one, you need to try at least 3 or 4 positions. So it's very long. It's very long, but the issue is that in biology, your system is alive, most often, and so the aberrations can vary in time, because your So because your sample can move, so you have breathing, you have blood flow, so if you are imaging at, let's say, 1 millimeter in depth or 500 microns, you have blood vessels on top, in between. And so you have blood flow, you have compression, you have plenty of effects. And actually, the correlation time can be quite slow in biological system. It means that you need to make your measurement faster than this correlation time. So this is doable for turbulences in the atmosphere. This can be quite challenging for biological samples. So of course, you can divide it into different kind of aberrations. Basically, if you want to image in depth, you will have mostly kind of a spherical aberration or stuff like this, because you are imaging not in water, but in different medium. But you also have some aberrations that vary quite quickly. And on so in astronomy, the same correction is working for various stars, but this is not the case because they are at the infinite. But this is not the case in microscopy. And when you go deep, the area where the correction is working can be very slow. So this is called the isoplanatic patch, and it can be only a few microns when you go deep. And so what you can do, if you want to correct nicely for aberration in depth, is that then you also divide your field of view into different regions, and for each region, you find the best wavefront to correct for aberrations. So this means that for each of this region, you did some iterative measurement to do it. So then it's quite challenging to do it quickly. But this was only with ballistic light. But actually, scattering is also deterministic. And if you have enough degrees of freedom, you can use the same device and you can shape light in order to refocus after scattering sample. So basically, if you have like a plane wave that you shine on a scattering medium, after that, you have a speckle. But if you have like a deformable mirror with a number of degrees of freedom high enough, you can refocus after that. And basically, the strength of your focus is given by the numbers of degrees of freedom that you can control. You can do it for 1 position, for 2 positions, 3 positions, but you can also do some generalization of this effect and transmit some information into a scattering medium by just sending with a deformable mirror or spatial light modulator some image into a scattering medium. But it is just a side note to go beyond aberration correction. Okay, and now I will talk about how to increase the amount of information in an optical system. So this quantity can be defined as the spatial bandwidth product, SBP, which is simply the field of view, so the size of the image you got, divided by the spatial resolution, and you square, because you have a 2D image. So there are some prefactors, but basically all the physics is here. And if you run the numbers, you can see that for different microscope objectives, this can vary from 4 to 37 or up to 100 million pixels. So microscope objective can transmit a lot of information, basically. But right now, scientific cameras, I mean good ones with high sensitivity, they have still a limited number of pixels. Let's say 1 to 10 megapixels. So of course you can find cameras with 100, 150 megapixels, but right now they are still very expensive as not as sensitive. Meaning that in an optical system, what limits your amount of information is your detection. Or if you take this picture, basically your objective can transmit a large image at high resolution, but your camera, if you want to correctly sample it with an equi sampling, you only image a tiny part of it. So this is what limits the amount of information in your system. So ideally, you want these two to match. Okay? So in our case, we are limited by the camera. For instance, in a cell phone, this is the opposite. Now you have cell phones that have like 100 millions of pixels, but they have still crappy objectives. So maybe it's not useful to have that many number of pixels. And so there are several ways to increase the amount of information. The simplest one is just to move the sample. You capture a sequence of image, and you do some stitching, some mosaic. And by doing this, you can have images that are like gigapixel images. But yeah, there is no field of view limitation. You don't have any aberration because you image only the center of your image, but it's really slow. There is another strategy, because I said that the objective is transmitting a lot of information, but the camera is limiting. Basically, a lot of information is scattered by the side of the camera. So here, if you use a tilting mirror, here, just before the camera, you can redirect the part of the images that were on the side of the camera to the center. And by doing this, you can capture also a sequence of image. And you can do some stitching, and you retrieve a really enlarged image. So here, you are limited. Before, by moving the sample, you can do this unlimitedly. But here, you are limited to the objective field of view. Basically, you can capture sequentially all the information transmitted by the objective. But you can have some aberration on the side. The advantage is that this technique is very fast, because here you just move a mirror. So in less than 1 second, you can capture this image, while by moving the sample itself, it can take minutes. So at least you are one order of magnitude faster. There are other more direct techniques to increase this spatial bandwidth. So the first one is to build a better microscope objective. So this is called the mesoscope, and this is like huge. So this is made on purpose by a group in the UK, and with such an objective, they have like a huge field of view with a good resolution, and so they have a spatial bandwidth product which is like huge. You can also work on the detection part, because if you have this amount of pixels, so you can collect it with a confocal, but it's going to take a lot if you do it point by point. Or you can use cameras with more and more pixels. So right now, they are not as sensitive as good scientific cameras, but it's getting better. But they are like pretty big. For instance, this is like a 2 megapixel camera on top of a 150 megapixel camera, which is pretty big, pretty expensive, but can be useful for such application. Or you can also use an array of cameras to parallelize your detection, and this is also doable. But this was all in the spatial domain to increase the spatial bandwidth product, but you can do it also in the Fourier domain. So there is a technique called Fourier ptychography. So it's not the same as a ptychography as performed in other domains, but the idea is to perform a fusion of low-resolution images taken for different illumination angles. So if you have a sample, you have like a bright field microscope, and if you have like a regular bright field illumination, you end up with an image, you take the Fourier transform, you look at the spectrum, and you have something which is centered around the 0 frequencies. So you have an expected circle. But now, if you change the illumination, if you tilt it, and you perform the same thing, you will end up with a spectrum which is shifted in the Fourier domain. And so, of course, you want to do it several times, let's say 50 or for 100 different illuminations. You do it, and then what you can do is you do some phase retrieval, but you do some fusion in the Fourier domain, then inverse Fourier transform, and you end up with a very large image at very high resolution. And by doing this, the idea is to take a low resolution objective, which has a very large field of view, but bad resolution, but to fill the Fourier plane iteratively by doing this. And so, for instance, here, this is an image taken with a 2x microscope objective, so like very, very low, but they end up with the same resolution as a 20x objective with, let's say, 100 images. So you have a huge spatial bandwidth product gain. You don't need to scan your sample, so this is pretty fast because you just change the illumination, take images. The limitations are that it's not compatible with fluorescence, and it works only with thin samples. So if you have a 3D sample that scatters light, it's not working, or not working well. And finally, there is also another techniques which use a structured illumination. So it's not angles, but you use a pattern on your illumination. And as we saw this morning, if you superpose an illumination pattern with a sample, you can have moire effect. And this can make frequencies that were not able to capture before. Now it's put back in the spectrum that you can measure. So if you have the spectrum of your sample and you illuminate it with a sinusoidal illumination, which has this kind of spectrum, then you end up with this kind of convoluted spectrum of the product of the two images. And of course, by changing the orientation of your sinusoid, you can really increase a lot the Fourier domain of your microscope, and you can increase the resolution of your system. So the practical implementation of this is simply putting a diffraction grating conjugated with your sample. So by doing this, you have a sinusoidal information, and then you just rotate, for instance, your diffraction grating. And this is an example from the Mats Gustafsson paper, where here this is a Fourier spectrum of a regular image. This is when you do some structured illumination. So I don't know if you see it, but on the sides, there is more content. And this is for a given structured illumination. And now you do it for various position of your grating. And by recombining them in the Fourier domain, you can double your spatial resolution. So here you need between 9 and 15 images to double the resolution. So this is pretty good. This is a good advantage, is that it's compatible with fluorescent light, which was not the case of ptychography, for instance. And it's also, there are some non-linear version of structured illumination microscopy to multiply the resolution by 3, 4, 5, but you need a huge number of images, and this is not as practical as a linear structured illumination. And so this leads me to my conclusion. So optical microscopy is in this region where we have a resolution initially between 10 and 1 micron, and we have a penetration depth which is at best 1 millimeter. But recent efforts are pushing towards deeper imaging without losing the resolution. So this is mostly 2-photon microscopy, 3-photon microscopy. I did not talk about it because there will be a talk on it, but you can couple light with sound. You can also do some clearing to image deeper, but this is working only for dead samples. Basically, you remove all the proteins on your sample, and then it's transparent. And the other trend is really getting better and better resolution in depth. And this is really challenging. And here, most of the techniques focus on super resolution plus adaptive optics, because super resolution is really sensitive to aberrations and scattering, and so they need to correct with adaptive optics to get below 1 cell. And there is also some expansion microscopy, but it's also working only with dead samples, where the idea is just to expand your sample, and then you win you gain some resolution. Just a little word about what I'm currently interested. I'm doing a lot of high-speed imaging on biophysical systems. So all of the aggregates that I showed are developed in our lab, and we use the microfluidic techniques to produce it. And actually, we use the Rayleigh plateau instability, which consists in the breaking of a jet into droplets. And here, our jet contains both polymer and some cells inside. And here, it's 300 microns each droplet. And then we have a calcium bath here, and this, when it enters the calcium bath, we have a capsule, and the cells are inside. And then they can grow for days or weeks. And what we want to do is to have a really monodisperse population of organoids like this. So we are interested into this instability, to control this instability with electric field, with other parameters. So that's one part of my activities. And I'm also working a lot on light field microscopy, which is a technique to perform single-shot 3D imaging. So the idea is to, in the detection part of a conventional microscope, you just add a micro-lens array in front of your camera. And then you have an image which is really weird at first, but by doing this, it contains both spatial information and angular information. And then you can do some interesting computing to extract different perspectives on your sample to perform some pseudo 3D in a single shot on our sample. So this is some cyst of stem cells, for instance, that are taken in a single shot, and then we can do some 3D imaging on it. And thank you.